Okay, let's talk about a fundamental challenge for these huge language models these days. You give them a massive document, right? A long report, maybe even, I don't know, a whole book section. And somewhere in there is the one crucial piece of information you actually need, that classic needle in the haystack.
Right.
And even these incredibly powerful models, they can really struggle to reliably find that specific detail, especially when the context gets really long.
Yeah, and researchers often trace this back to something they call attention noise.
Attention noise.
Exactly. The attention mechanism is, well, it's how the model figures out what parts of the input matter most for what it's doing right now. It assigns weights, basically.
Uh-huh.
But when the input is super long, that mechanism can just get sort of overwhelmed. It ends up giving some weight to pretty much everything, including a lot of irrelevant stuff. And that, well, it can drown out the really critical signals.
Yeah, it's like trying to pick out one specific voice in a huge echoing room or something. The standard attention hears something from everyone, but that just makes it harder to focus on the voice you actually care about.
That's a good analogy.
So the big question then is, how do you build an attention mechanism that's not just powerful, but also, selective, quieter, maybe?
Hmm.
And that's exactly what this deep dive is all about today. We're going to unpack a really cutting edge architectural idea called the differential transformer. And then, maybe even more importantly, we'll explore a very clever, practical way to bring its benefits to the massive LLMs you're already familiar with. It's called differential extension, or DEX.
Right. And the material we're digging into for you today comes from a stack of sources put together specifically for this deep dive. We've got a recent academic preprint, a briefing document that really breaks down the core concepts, and also a study guide that outlines the empirical results, the proof.
So our mission here is to cut through these sources, really understand the core innovations behind both that original differential transformer idea and this new DEX approach. We want to get into the academic insights about why it works and figure out what it all means for, how we build and use language models, especially for these long context tasks.
Yep. Get ready to get well informed.
Okay, so let's start right there with that core problem you mentioned, attention noise, the struggle with long contexts. What exactly makes standard transformer attention vulnerable to this?
Well, the sources explain that even the best models today, models that are amazing at understanding relationships between words, they still hit a kind of wall when you ask them to retrieve key information from really long documents.
Right?
Standard attention uses the softmax function. And the key thing about softmax is that it always outputs non-negative scores, 0 or positive.
Meaning everything gets at least some attention.
Exactly. Every single token in the context gets some attention weight, even if it's absolutely tiny. Now imagine you've got, say, a 4,000 token document. That's 4,000 different things the model is trying to pay some attention to for every single token it processes.
Wow, that's a lot of diffuse focus.
It really is. And it makes it incredibly hard to really zero in on that one specific piece of information, that needle.
Okay, so everything gets a participation trophy in the attention game, which just creates this constant low-level hum of noise. And the first big attempt to tackle this, according to the research we have here, was the original differential transformer, the diff transformer. What was the core architectural change they made there?
So the diff transformer was designed specifically to be less susceptible to all that noise. Its key innovation was something called differential attention.
Differential attention, okay.
Instead of using just one set of query and key projections to calculate those attention scores, like standard transformers do, it uses two separate distinct sets, Q1K1 and Q2K2.
Two sets, and then?
And then it computes the difference between the attention scores generated by these two sets. And it scales that difference by a learnable parameter, lambda, for limbing.
Huh. Like a differential amplifier, maybe? Amplifying the signal by subtracting out the common noise?
That's a really good way to think about it, actually. The paper explicitly states the goal is boosting attention on key tokens while suppressing common noise.
Makes sense.
The formula they give is essentially softmax Q1KJB, softmax TV. So by taking that difference, the idea is that patterns common to both attention computations, essentially the background noise, they should cancel each other out.
While the unique signals, the important bits, stand out more.
Exactly. They should become more prominent.
That architectural idea, yeah, it feels pretty intuitive for noise reduction, but what's really fascinating, and this seems to be where the core academic contribution lies, is that the research didn't just propose the architecture and say, look, it works. They really dug deep into why it performed so well in their experiments.
Absolutely.
And this is where we get some really deep insights into how attention maybe should work ideally. So let's dive into those deeper whys.
Definitely. This is where the analysis, this really interesting. They pinpointed 3 key reasons for the def transformer success that go beyond just that simple noise cancellation idea.
Okay, first one up. Enhanced expressivity via negative attention. Negative attention, that sounds weird. How can you pay a negative attention to something?
It does sound wild, doesn't it? Standard softmax attention, as we said, only produces positive or 0 scores. Everything gets some weight or none.
Right.
But their analysis, and they show this quite clearly in figure 3 of the paper, it reveals that different attention actually assigns negative scores to a pretty significant chunk of context tokens, especially in the higher layers of the network.
Whoa, so it's not just ignoring irrelevant stuff by giving it 0 weight.
No.
It's actively pushing it away, assigning it like a negative relevance.
Precisely that. It's not just about sparsity, which is setting irrelevant weights to 0. This gives the model a whole new dimension of control. It's the ability to explicitly penalize or downweight information that isn't just irrelevant, but maybe actively misleading or unhelpful for the task at hand.
Okay, and what's the consequence of having this negative knob to turn?
Well, this added flexibility gives the model a much more expressive way to contextualize information. The sources suggest it actually reduces the burden on what's called the output value matrix, the OV matrix.
Okay.
In standard models, that OV matrix has to implicitly try and filter out all that noise coming from the always positive attention scores.
Ah, I see.
By allowing negative attention scores, the transformer basically offloads some of that filtering job to the attention mechanism itself. And that leads to richer, more nuanced representations. Figure 4 has some cool examples of this.
Like what?
Like you see different attention assigning negative weights to an incorrect subject in a sentence, which helps the model correctly identify the true subject. Or, another example, downweighting literal interpretations of words to help it understand sarcasm better.
That's a really fundamental insight then. Attention isn't just about focus, it can also be about active suppression.
Exactly. Suppression could be just as important.
Okay, that's fascinating. What's the second key finding about why death worked so well?
The second major insight is about redundancy among the attention heads. Multi-head attention is powerful.
Right, standard practice.
Various studies have shown that sometimes different heads end up learning very similar patterns. They're essentially duplicating effort.
Like having several people on a team all doing the exact same analysis? Not very efficient.
Exactly that. And the analysis in these sources shows that different attention significantly reduces this kind of redundancy. Figure 5 illustrates this. It shows a higher cosine distance between the attention scores from different heads.
Higher cosine distance means they're pointing in more different directions, learning different things.
Precisely. The patterns learned by different heads are more distinct. They also show lower-centered kernel alignment, or CKA, between the feature representations coming out of the different heads.
Okay, CKA. Lower CKA means what in simple terms?
Think of CKA as like a similarity score between the internal understandings or representations learned by different parts of the network, in this case, different heads. A lower CKA score between heads means they are learning and contributing more distinct types of information to the overall picture the model is building.
Got it. So lower CKA, higher cosine distance, it means the heads aren't all just echoing each other. They're not stepping on each other's toes.
Right. And this reduced redundancy, combined with a more balanced contribution across the heads, they also show head importance, is more uniform in figure 6. It means the diff transformer can capture a broader and more diverse set of features from the input, which leads to a richer, more comprehensive understanding overall.
Makes sense. More diverse perspectives are usually a good thing. Okay, and the third key reason, this one sounds intriguing.
This one is really fascinating, yeah. It's about the training process itself, the learning dynamics. Training these really deep networks, it can be tricky. You can get stuck in suboptimal spots in what's called the optimization landscape.
Optimization landscapes sounds bumpy.
They can be very bumpy, exactly. Lots of tricky spots. But the diff transformer seems to navigate this landscape better. The sources include an analysis of its Hessian spectra, which is basically looking at the curvature of this optimization landscape.
Okay.
And they find significantly fewer negative eigenvalues in the Hessian compared to standard transformers. That's shown in figure 7.
And fewer negative eigenvalues tells us, what about the landscape?
Generally, it indicates a smoother landscape for the optimization process. It means the training is less likely to get stuck in difficult saddle points or sharp local minima.
Ah, so it leads to more stable training?
Seems so. They also show more stable gradient norms during training in figure 8, which supports that idea.
And this is where it gets really interesting, you were saying, because the architecture itself seems to make learning easier.
It really does seem that way. And the research suggests that the learnable scalar, LLM member, plays a really crucial role here. It seems to help stabilize the training, especially in those critical early phases.
So Lambda isn't just a tuning knob, it's actively helping the training process itself.
It appears to be actively contributing to smoothing out those learning dynamics. It's quite a finding.
Okay, so summing up the original diff transformer, we've got the expressive power of negative attention, reduced head redundancy leading to more diverse features, and a better behaved, smoother training process. That sounds amazing.
It really does offer significant advantages on paper and in their experiments.
But there's always a bet, isn't there? There's a major practical riddle here, right?
Exactly. The big catch is that the diff transformer's architecture with those dual query key pathways, it's different enough from standard transformers that you can't just, take its attention mechanism and easily drop it into an existing powerful pre-trained LLM.
Like a llama model or Quen or GPT.
Precisely. You'd have to train a diff-style model basically from scratch.
Which for models with billions, maybe trillions of parameters, that's astronomically expensive. Time, money, compute.
Hugely expensive. And crucially, you lose the immense benefit of all the knowledge baked into those models from their original pre-training on vast amounts of text.
Right, there's this architectural gap, as you called it. It prevents you from easily transferring those cool diff benefits to the models everyone is actually using and building on today.
Yep, that's the core problem they set out to solve next.
And that's where differential extension, or DX, finally comes into the picture.
Yes, DX is the novel framework proposed in these sources specifically designed to bridge that exact gap. Its main goal, its objective is, and I'm quoting roughly here, to inject the strengths of the diff transformer into a pre-trained LLM without training from scratch.
Okay.
And it's designed with key requirements in mind. It needs to be effective, obviously, but also lightweight, minimal extra parameters, minimal computational overhead, and critically, it absolutely has to preserve that valuable pre-trained knowledge.
Okay, so how does DX pull this off? How does it manage to capture the essence of differential attention and all those benefits we just discussed? Negative attention, less redundancy, using those insights from the original diff model, but without fundamentally changing the query key structure of a model that's already been trained. This sounds like where the really practical innovation happens.
Right, this is the clever part. The key idea is what they term implicit differential adaptation.
Implicit adaptation.
Yeah. They recognize you can't easily just split or duplicate the query key projections in a pre-trained model to create those dual pathways like in the original diff. Doing that would likely just break the model's carefully learned representations, or it would add a huge computational cost, or both.
The existing weights are already finely tuned for that standard single QK setup. You can't just mess with that core part.
Exactly. So instead of altering the fundamental QK computation, DEX applies its learnable differential mechanism after the standard softmax attention calculation. Specifically, it targets the output of the attention block, the OV matrix. You can see this in figure 9. The formal update looks like O equals OAFDO, where O is the original output and FD is the differential function.
Applying the differential idea to the output matrix, why does that work? How does that capture the diff benefits?
This implicit approach is really smart, and it's actually grounded in an observation they made when analyzing the original diff model. They found that the magnitude of the standard softmax attention scores actually correlates pretty well with the magnitude of the diff attention scores. Figure 14 shows this.
Meaning
the pre-trained model already kind of knows which tokens are important. That high magnitude signal is already there in the standard attention output.
okay. The base model has the what's important part down pretty well.
Exactly. So DX leverages this existing strong magnitude signal. By applying its differential operation on the output pathway, the OV matrix, which we know already does some implicit filtering anyway, DX essentially refines how that important information gets processed and combined. It effectively introduces the differential concept there without needing to mess with the upstream QK calculation that deteriorated the initial important signal.
So it reuses the strong what's important signal from the pre-trained model and then adds this clever how to refine and maybe suppress noise step right at the end of the attention block. That's very neat.
It is quite elegant.
And building on that insight about head redundancy we talked about earlier, DeepX also has an innovation there too, right? Selective adaptation.
Yes, exactly. Innovation number 5, selective adaptation. As we discussed, standard attention heads in a layer are often heterogeneous. Some are really critical doing specialized jobs, while others might be less specialized, maybe even a bit redundant.
Right. Not all heads are created equal.
DEX takes advantage of that inherent variability.
How so? How does it use that?
Well, instead of applying its differential mechanism, that O0FDO update, to all the attention heads in a given layer, DEX applies it only to a carefully selected subset of heads. Figure 9 shows this targeting H heads out of the total.
And how does it choose which heads to target?
It typically targets heads that are identified as potentially less critical or maybe underutilized. They mention using metrics like lower importance scores or, interestingly, higher attention entropy.
Higher entropy suggesting a head that's kind of spreading its attention around more, less focused, less specialized, perhaps?
That's the intuition, yes. A head with high entropy might be a good candidate for this kind of enhancement. So by applying the differential adaptation selectively to these potentially underutilized heads, DEX aims to enhance their capabilities, maybe make them more specialized or better at noise reduction. And the goal is to boost the overall representational diversity and capacity of the model without interfering with the crucial, highly specialized knowledge already captured by the other untouched heads.
It's like giving targeted coaching or a specific new tool only to the team members who might benefit most, improving the team's overall range without disrupting the star players.
That's a really good way to put it.
Okay, makes sense. What's the final key piece of the puzzle for how DX works? Something about stability.
Yes, innovation number 6, balancing adaptation and stability with lie annealing. This addresses a very practical problem. When you introduce a new learnable parameter like lie annealing into a massive, finely tuned pre-trained model, things can get unstable.
Right.
If you initialize that new parameter legs too weakly, say close to 0, the model's existing knowledge is so strong it might just ignore the new mechanism completely during fine-tuning. It never really learns to use it. But if you introduce it too strongly or too abruptly, it could destabilize the whole fine-tuning process, potentially harming the existing knowledge.
Navigating that bumpy optimization landscape again, but this time during the adaptation or fine-tuning phase.
Exactly. So to handle this delicate balance, DX employs a pretty carefully designed annealing schedule for that learnable labs. Equation 4 describes it. Basically, it starts the influence of the learned lab at 0, ensuring stability at the beginning of fine-tuning. Then it gradually introduces the differential signal using an annealed constant value for lambda, which is inspired by the magnetate observed in the original diff work. This provides a consistent learning signal early on.
Okay.
And then, over the course of the fine-tuning, control smoothly transitions from that annealed constant to a fully learnable parameter. This allows the model to fine-tune land to the optimal value for the specific task and data. Figure 11C shows this schedule quite nicely.
That gradual handoff from 0 to a guided constant to fully learned, that seems really critical for stability when you're tweaking these huge pre-trained beasts.
It really is. The sources emphasize that this carefully crafted schedule is crucial for balancing the need to preserve that massive amount of pre-trained knowledge with the need to effectively introduce and learn this new differential mechanism. It's a key part of what makes DX practical and effective for adapting existing models.
Okay, so putting it all together, we have DX. It's a lightweight framework built on these deep academic insights about why differential attention is powerful. It uses implicit adaptation on the output, applies it selectively to less critical heads, and uses a smart annealing schedule for lambda to ensure stability during fine-tuning.
That's a great summary.
The big question now, the one you really care about, is does it actually work? Does it deliver in practice? What do the sources show in terms of empirical results?
Right, this is the payoff. And the results reported are actually quite compelling. This is why you should care. It shows these innovations aren't just theoretically, they translate into real-world performance improvements.
Okay, let's start with standard language modeling performance. How does DX do on typical benchmarks?
Across various LLMs, they tested Llama family, Quinn family DEX substantially improves performance on standard language modeling benchmarks. But here's the really remarkable part. It achieves these gains using minimal adaptation data, like less than 0.01% of the data used for the original pre-training.
Less than 0.01%. That's tiny.
It's incredibly small. Table 1 and Figure 13 show these results. The research notes that DEX often outperforms other popular lightweight fine-tuning methods, like LoRa array, or even full fine-tuning when everyone is restricted to this tiny amount of adaptation data.
Wow.
And they specifically highlight strong improvements on tasks like WSC, the Winograd Schema Challenge.
Ah, that tests pronoun resolution, right. Figuring out who he or she refers to in tricky sentences.
Exactly. And that's a task that seems to directly benefit from the ability to downweight incorrect possibilities, which really aligns nicely with that whole negative attention concept we discussed earlier.
Minimal data for substantial gains, especially on tasks that seem linked to its core mechanism. That's a huge practical win. Okay, how about that needle in a haystack problem we started with? Does it help with long context information retrieval?
Yes, significantly. On the needle in a haystack benchmark, which explicitly measures this ability, DEX shows really notable improvements. Figure 10 highlights, for example, an 11.4% average accuracy increase on a Llama 3B model in one common setup of that test.
That's a solid jump.
It is, and the analysis confirms why it's working better. Table 2 shows that DX successfully directs more effective higher attention scores to the specific token spans that actually contain the answer, even though it's adapting implicitly on the output.
So it is helping filter out that background noise and focus attention better, even with the implicit approach.
The evidence suggests so, yes. It seems to genuinely help the model find the right information when it's buried in the dense context.
What about in-context learning, the ability to learn from examples given in the prompt?
There too, it consistently delivers performance gains across different benchmarks and various few-shot settings compared to both the original base models and other fine-tuning baselines like LoRaWoW. Table 3 lays this out.
So it seems to improve the model's ability to quickly adapt and learn from the examples you provide right in the prompt itself.
That's what the results indicate.
Okay, performance looks good, but for practical deployment, efficiency is always key. How does DX stack up in terms of speed and overhead?
Yeah, this is important. DX was designed from the start to be lightweight, and Figure 12 shows that its test time throughput, how fast it can process text, remained very competitive with the original Llama model it's based on.
So no major slowdown at inference time.
Not according to their results. Unlike the original diff transformer architecture, which could theoretically become less efficient with very long context due to the dual computations, DX avoids that potential bottleneck because it applies its change after the main attention calculation.
And the parameter overhead. How many new weights does it add?
Minimal. They emphasize it's a very lightweight adaptation in terms of parameters added.
Okay, that's crucial for practicality. And the sources, they usually include ablation studies, right, where they test removing different parts of their method. Do those studies confirm that the specific design choices in DEX, like which heads to target, or using that whole annealing schedule for lambda, are actually important?
They absolutely do. That's in Table 4. The ablations show that using their entropy-based strategy to select which heads to adapt is important performance drops if you just adapt random heads, for instance.
Okay.
And they also show that using the full annealing schedule we discussed is necessary for getting the best performance. If you remove parts of that schedule, like just using a constant lambda or only the learnable part, performance suffers.
So the specific details of their method matter.
Yes. The analysis also confirms that DX is indeed modifying the attention output O as intended, that's figure 11A, and figure 11B shows it successfully reduces interhead redundancy, measured by CKA, within those adapted heads, just like the original diff inspiration suggested it should. Figure 11C validates the annealing schedule's effect on lambda's value during training.
That analytical conversation really strengthens their claims about how DX is achieving its results. It's not just a black box improvement.
Exactly. The ablation studies and analysis really back up the specific design choices they made based on the insights from the original diff work.
Okay, so wrapping this all, then we've gone deep into the problem, the original solution, the analysis of why it worked, the practical limitations, and this new DEX approach with all its components and results. What are the key takeaways here? And did the sources mention any limitations we should keep in mind?
Yeah, they are quite clear about limitations, which is good scientific practice. They note that the detailed analysis of the original diff transformers mechanisms, like the negative attention and redundancy, was done on a smaller model they trained themselves because the weights of the original larger diff models weren't available for that kind of deep dive.
Okay, so the analysis underpinning DX was on a smaller scale model.
Right. And DX itself, while tested on models up to 8 billion parameters in the Llama and Quen families, hasn't yet been evaluated on, say, truly massive models like 100 billion parameter scale or beyond.
So performance might vary at much larger scales, or maybe with different types of pre-training data?
It's possible. Those are fair points to acknowledge. It's a very strong showing in their experiments, but not necessarily a claim of universal applicability without further testing.
Understood, but despite those limitations, the overall significance seems pretty high.
I'd say so, yeah. The overall significance here is really twofold. First, this work provides rigorous, empirically supported insights into why differential attention helps models digging into the power of negative attention. the benefits of reduced head redundancy, and even improved learning dynamics. That's valuable knowledge in itself.
Understanding the fundamentals better.
Exactly. And second, and perhaps more immediately impactful, DEX offers a practical, efficient, and genuinely lightweight method to take those sophisticated benefits derived from analyzing a novel architecture and successfully apply them to improve existing, powerful, pre-trained LLMs that people are using right now.
And it does this bypassing the need for that incredibly expensive training from scratch.
Completely. It provides a really smart architectural adaptation strategy. You get substantial performance improvements, especially with limited adaptation data, and with minimal computational cost at test time. It's a lot of bang for very little buck, so to speak.
This deep dive has really hammered home, for me at least, that significant innovation in LLMs isn't always just about scaling up bigger and bigger, or only about building completely new architectures from the ground up. It's also about this really intelligent adaptation, understanding the principles of why something works in a novel design, and then finding clever, efficient ways to graft those principles onto the incredible foundation that already exists in these massive pre-trained models.
It's a very promising direction for progress, I think. A different kind of innovation?
Definitely. So to leave you, our listener, with a final thought to maybe mull over, think about the potential here. We're seeing ways to take cutting-edge insights from brand new architectures, ideas like differential attention, and find these smart, lightweight methods to integrate them into the huge, powerful models we already have. Could this kind of targeted, efficient architectural adaptation become a major pathway for rapid LLM improvement moving forward? Could it unlock capabilities that were sort of latent, hidden within these existing models, all without needing another budget-busting, multi-million-dollar training run from scratch?
It's certainly a fascinating possibility for the future of the field.